All right, let's talk about something truly mind-blowing. We're going to pull back the curtain on how your computer, specifically your GPU, performs miracles. We're diving into its two secret weapons, two algorithms called reduction and scan. These are the techniques that let GPUs just chew through mountains of data. Ready? Let's get into it.
So let me just start with a question. How in the world do you add up a billion numbers? Not in a few minutes, but like right now, in the blink of an eye. You know, a normal processor would just go one by one by one, which would take forever. But a GPU plays a completely different game.
And that's the whole secret right there. It's not about one core working harder, it's about thousands of tiny cores all working together. Instead of one person doing all the work, imagine a 1,000-person crew showing up to tackle the problem all at the same time. It's a total shift from working in a single file line to, well, teamwork on a massive scale.
And the two star players in this parallel universe are reduction and scan. These are the fundamental building blocks, the power plays, that let developers turn those slow step-by-step chores into these incredible, lightning-fast victories. So let's get to know them.
First up, we've got reduction. And its name kind of gives it away, right? Its whole job is to reduce a giant list of data down to just one single answer. So think about finding the absolute highest temperature recorded across a million sensors, or finding the average color of every pixel on your screen. That's a reduction.
And then we have its partner, scan. You might also hear it called a parallel prefix sum. Now this one's a little different. It takes an array, and it spits out a new array of the exact same size. But here's the really cool part. Every element in that new array is a running total of the original. So the fifth element in the new list is the sum of the first 5 elements from the old list. It's like a cumulative report card at every single point.
Okay, so putting them side by side like this really makes it click. Reduction is all about getting to one final answer, a single number. Scan is about the journey. Its goal is to create that whole new list of running totals. And that running list? That's the secret sauce for all sorts of advanced stuff, like organizing or filtering massive amounts of data in an instant.
So how on earth do thousands of these little processors work together without just tripping all over each other? The method is surprisingly elegant, and honestly, you can think of it just like a sports tournament bracket.
So let's look at reduction first. Imagine all your numbers lined up. In the first round, the algorithm pairs them up. Then, bam, thousands of GPU threads all jump in and add their assigned pair at the exact same moment. Then it takes all those winners, all those new sums, and pairs them up for the next round. And it just keeps doing that over and over again. And this quote just nails the idea. It really is like that tournament. Teams play, winners advance, and the field gets smaller and smaller with each round. It keeps combining and combining until there's only one champion left standing, the final answer.
Okay, so what about scan? Well, scan is kind of like a 2-act play. The first act is called the upsweep. And here's the thing, it's going to look really familiar, because it works exactly like the reduction algorithm we just covered. It pairs things up, builds this tree of partial sums, and works its way up.
But this is where the magic happens. In Act 2, the downsweep, the algorithm takes all those partial sums it just created, and it works its way back down the tree. And as it goes, it distributes those totals, cleverly filling in all the blanks to create that final, perfect array of running totals. It's a really slick 2-step process.
So this all sounds pretty academic, right? But what does it actually do for us? Well, turns out, these algorithms aren't just for math problems. They are the engines running behind the scenes in some of the most demanding software on the planet.
I mean, just think about it. Reduction lets financial firms calculate investment risk across millions of portfolios, like right now. In science, it can track the movement of thousands of particles in a simulation. And scan? Scan is the unsung hero powering super-fast sorting, filtering huge data sets by compacting the information down to only what you need, and even helping manage computer memory on the fly.
And here's the real kicker. We are not talking about a small speed boost. We are talking about taking computational tasks that would have taken hours on an old-school processor and absolutely crushing them in milliseconds. This isn't just doing things faster, it opens the door to solving problems that were basically impossible before.
But, and you knew there was a but coming, right? This kind of unbelievable speed doesn't come for free. To get all these thousands of threads to work together perfectly, you've got to be really careful. It comes with its own set of challenges. To make this work, developers have to play conductor for this massive orchestra. They're balancing the number of threads with the size of the data. They have to use the GPU's super fast but very limited shared memory wisely. And maybe the most important thing of all is synchronization, making sure all the threads wait for each other at the right time so you don't get chaos.
And if you get that conducting part wrong, the results can be disastrous. You could get an answer that is just flat out incorrect. Or, and this is the really ironic part, for smaller problems, this whole complex setup can actually be slower than just doing it the simple, old-fashioned way. Getting top speed requires some seriously specialized code.
So here's the real takeaway. The mind-bending power of parallel computing isn't just a switch you flip. It's a power that has to be unlocked through really careful, really clever design. It's a testament to the engineers who write this code and orchestrate this beautiful, complex dance of data and processors.
And that leaves us with a pretty cool thought to end on. By mastering things like reduction and scan, we've basically taught computers how to think in a massively parallel way. It's a fundamental change in how we attack big problems. So it really makes you wonder, now that we have this power, what problems that we once thought were completely impossible are we going to solve next?